Thank you. I'd like to thank the organizers for inviting me. It's always a pleasure to come to Sweden, especially in the winter, but the spring can be nice too. I was asked to speak on my view of the current state and future of fundamental physics. I took that to mean high-energy physics and cosmology. Maybe that was an error here, but that's what I took. And furthermore, after Fabio Zwirner's superb talk about prospects at the LHC that covered many important aspects, I was left with only a little bit to talk about, but I'm going to talk about a few subjects that are especially close to my heart. I will start with a word of warning that my perspective is very much a zero-brain perspective. That's B-R-A-N-E. And without further ado, 3 ways that I see we should be going beyond the standard model. I will discuss quantitative unification, axions, and portals. The standard model is astoundingly successful, but it clearly has major aesthetic flaws. It has several moving parts that are tenuously connected, several forces, several different kinds of disconnected fermions. Has many continuously adjustable parameters. Some of these shortcomings may reflect pure environmental accidents, the dreaded anthropic or landscape scenario. Others may not be entirely random, but conditioned by anthropic conditions. In those conditions, it may be difficult to maintain the traditional high standards of theoretical physics. We might be reduced to accommodating facts as opposed to constructively explaining them. In particular, in the case of trying to determine those continuous parameters that appear in the standard model. I'm sorry if I've caused offense. Somebody doesn't like anthropics or landscapes, I suppose. Anyway, we can identify, however, I think clearly, at least I feel it's clear, a few outstanding empirical facts that seem unlikely to be explained away along those lines. These include particularly the gauge group and multiplet structure of the standard model that practically beg us to construct a unified theory. And then, if we go ahead and do it, that it works quantitatively remarkably well. There are small but non-zero neutrino masses, I mean, very small compared to the other particles, so that's a qualitative fact. None of these facts appear at any reasonable level to be connected with the existence of intelligent observers, so there are things that even in a landscape picture we're required to try to understand. And the last one is the smallness of the QCD theta parameter. There may be others, but those are the ones that will appear in this talk. These facts have inspired truth-worthy theoretical proposals with wide-ranging implications. Truth-worthy, of course, is subjective. I mean things that deserve to be true. With the coming of the LHC and expected advances in observational cosmology, the trial date for those ideas is approaching, and that's what makes this an appropriate time, especially, to talk about it. I'll also, if time permits, mention another thing that I think emerges from the standard model, that the standard model suggests that only a few kinds of particular perturbations or new additions to the standard model are both plausible and accessible, and we can use that classification to guide our thinking about experiments and theories that hope to be relevant to experiment. Actually, it's not quite that good, or not that restrictive. These constraints really come in only if you demand that we're explaining the success of unification and the unification of couplings. And by no means are we led to a unique classification of possibilities, but only a sort of classification of what's not implausible and not inaccessible. Okay. Many of these ideas go back almost an unimaginably long way to the days of my youth, but there's been continuing ferment, new ideas, and I hope very soon new experiments. So it's a good time to talk about them. It's also appropriate, I think, to talk about it here because crucial aspects, as you'll see over and over again, remain vague and sketchy. So there's a big challenge out there to do better. So if you find yourself asking at some point, what does this all have to do with string theory? You're asking a very good question. Okay, so let me begin with quantitative unification. First, I'll quickly remind you of qualitative unification. This is the standard model as it comes, and as you all know, it would be difficult to exaggerate the success, the power, and the economy of the standard model in describing an enormous quantity of facts. But just because it describes such an enormous quantity of facts and appears to be so close to nature's last word, we have to judge it by very high standards. And by aesthetically high standards, this really doesn't look like an ultimate theory. We have 3 different forces. We have 6 different unrelated kinds of matter, unrelated by the symmetries of the standard model. We have these funny numbers hanging on the side, taken from experiment. And of course, I've left out gravity here and left out the embarrassing repetition of families that are observed. It's begging us to do better and also telling us a direction in which you can do better because it's based on gauge symmetry. So gauge symmetry is a very rigid structure. We know how you can extend it. And if you try one of the simplest possibilities for expanding the gauge theory of the standard model, it's very simple to see what kind of groups will support SU3 cross SU2 cross U1, of course. Much less trivial is the fact that the fermions fall into place, filling out very beautifully a spinor representation of SO10 and explaining those funny hypercharges that were hanging on the side that looked so ugly and arbitrary within the standard model itself. So this is a very striking regularity that's very robust. It depends really only on discrete quantities in the standard model. So clearly, we should try to put it into a consistent dynamical framework and try to draw further consequences from it. As you'll see, some simple ideas take us rather far and lead to testable consequences. Philosophers and Bayesian statisticians teach us that simplicity and testability are virtues. The standard model also has 2 great dynamical lessons that point us in a certain direction here and encourage us. The standard theories of superconductivity and of electroweak symmetry breaking show us how gauged spontaneous symmetry breaking can give reduced symmetry, reduce us from the SO10 or other unification group to a smaller symmetry of the standard model, and also lift the masses of the unobserved vector bosons, which would otherwise mediate dangerous unobserved processes such as proton decay. And the other great dynamical lesson of the standard model the renormalization group, shows us how the observed low-energy couplings might diverge from the universality or equality demanded by non-abelian gauge symmetry at high energies when the symmetry is unbroken. So we're invited to apply those two big lessons to this unification program. The big question is whether that program survives more detailed and quantitative scrutiny and whether it bears additional fruit. Famously, if we just use the degrees of freedom within the standard model, it doesn't quite work. The couplings don't quite unify. However, if we extend the theory to include the degrees of freedom required for approximate supersymmetry with masses of order 10 to the 2 to 10 to the 3 GeV, it works much better. That's a familiar and very attractive picture. We should be quantitative, though. To make it objective, let's consider what is the exact statement relating observables to theory, and how accurate is it? Well, I won't give you the exact statement, which is kind of complicated, but very much in the spirit of it and extremely close to the truth. We can just use the one-loop expressions, the first order, lowest non-trivial order expressions for how the coupling constants vary with scale. And then it's a matter of very simple algebra to prove that if you take the differences that are due to the evolution of these different guys and multiply by the correct beta functions or coefficients indicated here, that the prediction of unification is that this quantity, well, the prediction of these equations without anything is you get this relationship, and then where these differences are the quantities you get by subtracting one line from another with different values of j. And the prediction of unification is that at some large m, they all become equal. And then the expressions in these deltas, and these differences of deltas, just reduce to observable coupling constants at low energy. So this is a constraint among observables. And if we put in the numbers, it's not quite zero. But if we ask how big a fractional deviation from a single unified coupling is allowed, and call it delta J, then the constraint among the delta J's is that a total answer that involves numbers like 4, 10, and 6 has to sum up to 0.04. So it's an extremely impressive quantitative success, and I would be very reluctant to think that nature has such a low sense of humor that she's teasing us with this. The values, this calculation gives two outputs from the three inputs of the observed couplings, and the outputs are the value of the unified coupling and the value of the unification mass, and those are the values. It could have been something else in principle, and it's part of the success of this calculation that those values have very good features. First of all, the coupling is not terribly strong, so low-order calculations in perturbation theory are adequate to do an accurate calculation. Secondly, the coupling is not terribly weak. We expect something to be happening at that unification scale that's associated with breaking the symmetry, so we might have been disturbed if the coupling was extremely, extremely weak up there, but in fact it's not. A unified coupling of 1/25 is actually quite large. The scale is not too large. It's significantly smaller than the Planck scale, and therefore we, in the calculation neglecting quantum gravity, we don't manifestly run into contradictions. The scale is not too small. If it was significantly smaller, the exchange of the extra W bosons associated with the unification would lead to proton decay at a more rapid rate than is observed. So the unification scale had to fall into a narrow window, and it does. And it also gives reasonable input to the neutrino seesaw mechanism for generating those small neutrino masses that I alluded to at the beginning. So it's hard to ignore all this success, I believe. Also, you get a reasonably good, but not perfect, and this is definitely one of those places where we could use additional guidance from higher theory, unification also with gravity. Gravity, of course, famously, and this to me is the main problem with quantum gravity, and it's essentially solved, it initially starts out terribly, terribly, terribly weaker than the other interactions. Why, if they're going to be understood in a common framework? Well, the fact that we extract from logarithmic corrections a very large scale based on the observed couplings means that when we have power law corrections, as in gravity, the large lever arm we need for this unification gives us an enormous factor in the gravitational calculation, and in fact, it, within astrophysical accuracy, does give a unification. Now, this calculation is quite bold. We took just the degrees of freedom of the standard model and souped it up with low-energy supersymmetry. It may or may not be plausible that there's nothing else in between, but another strength of this calculation and another aspect of it and another reason that it guides, I think, sensible speculations is that it's not changed, the successes are not changed as long as you add complete multiplets under an SU5 symmetry, or of course any kind of SU3 cross SU2 cross U1 singlets, because only the differences between the different beta functions figured in the relevant calculations, and in the case of SU5, the difference would vanish. In the case of singlets, of course, both terms are zero. We can extend this to get, I think, other extremely interesting information and extremely tantalizing for near-future experiments. If the symmetry breaking terms that are necessary to give masses to fermions are of reasonably simple form, group theoretically under this unification, then we get additional predictions relating fermion masses. If we assume that the mass is of quarks and leptons are dominated by the expectation value of a field in the five-dimensional representation, a Higgs field in the five-dimensional representation, then we get the relationship at unification that the B quark Yukawa coupling is equal to the tau lepton Yukawa coupling. One could try to be bold and extend to lighter families, but that I think involves lots of ambiguities and is a higher order kind of boldness that I don't want to go into here. If we go further and assume 10 dominants in SO10 for the mass, for the underlying Yukawa couplings, then we get also that the top quark coupling is equal at the unification scale. Of course, these Yukawa couplings have to get renormalized and processed before becoming observables, before becoming quark and lepton masses. I didn't mention it, but yet another strength of the gauge coupling calculation is that it's quite immune, remarkably immune to low energy corrections, to splittings, for instance, between masses of different superparticles. But these results are not, the mass predictions are not. So you can read that as either saying, well, we can't quite make them quantitative today, or that they guide us, or we can't quite check them today, or that they guide us, give us constraints about what the low energy corrections are, which again will either be verified or not at the LHC. B-tau unification works reasonably well, and if you look at the details of the fit, suggests that gluino masses are significantly smaller than squark masses. In particular, the gluino masses are particularly smaller than the supersymmetric partner of the bottom masses. And also that the ratio of vacuum expectation values that appears in supersymmetry, where you have two Higgs doublets at the weak scale, the so-called tan beta parameter, should be much, much greater than 1. If you step it up to the B-tau T unification, this definitely requires a large ratio of vacuum expectation values. The only way that the underlying Yukawa couplings of the B and tau masses, B and top quarks can lead to such grossly different masses is if the vacuum expectation value relevant to the top quark is much larger than the vacuum expectation value is much larger than the vacuum expectation value relevant to the bottom quark. That translates into tan beta equals 50, certainly consistent with this hint, and even more strongly suggests this kind of inequality. With precise information about the low energy parameters, precise comparisons will become possible. So this idea of quantitative unification will go from being a kind of unique crown jewel of the standard model to a whole web of predictive relations that will make unification a rich precision science, if all goes well. Okay. Now let me talk about axions. First, let me check how my time is doing. Okay. So the other great unnatural fact that can't be explained anthropically and doesn't look random within the standard model is the smallness of the so-called theta parameter of QCD, a parameter that could have, but in fact in nature does not, lead to significant time reversal symmetry violation in the strong interaction. When you study numerically the constraints put on its value by the observed smallness of neutron electric dipole moments, specifically, you find that the absolute value of this parameter, which is an angle, could have taken any value between minus pi and pi, say, actually has a value that's less than 10 to the minus 9. And it's very hard to believe that anything about the existence of intelligent observers or the emergence of life or anything like that depends on this parameter being so small, if you think about it. How would life be different if the neutron had a significant dipole moment? Not very much. And so this is something we need to explain on other principles. It can be understood by promoting translation of theta, the ability to change theta into first of all, it can be understood, yes, by promoting this ability to translate theta to an asymptotic or classical quasi-symmetry, Peccei-Quinn symmetry, that's spontaneously broken. In other words, you expand the degrees of freedom of the standard model in such a way, roughly speaking, as to make theta a dynamical variable. And then if you do things right, when you minimize the energy, this dynamical variable chooses dynamically to be 0. More specifically, we have some order parameter field associated with the Peccei-Quinn symmetry that at some scale f acquires a vacuum expectation value, and its phase is effectively the theta parameter. If we canonically normalize the dynamical theta parameter in terms of a scalar field, we should put an A over F here, and that's the axion field. At the transition, the energy associated with varying the value of theta, or in other words, with variations in the axion field, is negligible compared to the enormous ambient energies at high temperatures in the early universe, and also at very high temperatures in the early universe, the dynamical effect of instantons, which is where energy dependence of theta arises, are suppressed. So the energy density associated with different values of theta is negligibly different, and in random events in the early universe, differences from the minimum value of theta can be imprinted. There's no cost, and to maximize entropy, theta takes different values in different places. Later on, as things cool down, the axion field will realize that it made unfortunate choices in the early universe that got frozen in, and then will start to evolve. And what will happen, it's been calculated, is that these fluctuations will materialize. They'll settle down to very nearly zero, so we really will have eliminated theta as a problem within the standard model. However, they will, in the process of relaxing, materialize as a substance whose density is roughly proportional to F sine squared theta 0 today. A substance, in fact, which looks like a gas of very, very light non-relativistic particles, the axions produced in an ultra-cold Bose-Einstein condensate. Now, here's the very simple calculation that goes into that. So we want to estimate the energy density today associated with a misalignment by theta 0 compared to the zero of energy at theta 0 equals 0. So this is a crude estimate of the energy in play. It gets diluted as the universe expands. Once it's materialized as non-relativistic particles, the energy density goes down like T cubed. In the transition between when it's frozen in as field energy and materialized as ordinary particles, there's a so-called adiabatic damping factor. This is the only subtle part of the calculation. It wouldn't be appropriate to review it here, but what I wanted to emphasize is the straightforwardness of this calculation and how the density today divided by temperature cubed, that is the measurable temperature of the microwave background, is related to simple fundamental parameters. If no inflation occurs after the Peccei-Quinn transition, then the correlation length at that transition, which can be no longer than the horizon length by causality, corresponds to a very small length in the present universe. Horizons back then are very much smaller than the horizons today. The universe has been expanding, and we can see more. So, when we look at the large-scale distribution of energy density in the universe, in this scenario, we should average over sine squared theta 0. We get to sample many, many different values of theta 0 that are statistically uncorrelated. That's an easy average to do. It's a half. And since we expressed the density relative to microwave background temperatures in terms of fundamental constants and the parameter f, we can calculate what value of f corresponds to the observed dark matter density, and it's about 10 to the 12th GeV. Experimental constraints on this axion field require that F is greater than about 10 to the 10th GeV. And remember, the density is proportional to F, and you get critical density if you average over sine squared theta 0 when F is 10 to the 12th GeV. So there's only a small window between the experimental bounds and the cosmological expectation here. And that's another way of saying that axions are almost forced to be an important component of the dark matter if they exist at all. So this makes it seem interesting to entertain the hypothesis that axions, if they have to produce a significant part of the dark matter density, they might produce most of it. That's traditionally been regarded as the default axion cosmology. It hasn't quite been tested yet, but the crucial experiments are underway. They're based on a sophisticated sort of antenna which converts the ambient axion radiation into more experimentally accessible microwave radiation by the process of A goes to photon-photon, where one of the photons is an external magnetic field. As I said, that's been the default axion cosmology until really the rise of inflation. If inflation occurs after the Peccei-Quinn transition, things are very, very different. Then the correlated volume, which before became a very small part of the observable universe, gets inflated and instead covers the entire observable universe. So that step of averaging over sine squared theta is no longer appropriate. And since the total density is F sine squared theta 0, we can accommodate larger values of than 10 to the 12th by allowing atypically small values of theta 0. Now, if you just think about different volumes in the inflated universe, we'll call it a multiverse because different parts of it have different properties, namely different amounts of dark matter because they start out with different values of theta 0. Then most of the multiverse is overwhelmingly axion dominated, and you can very rapidly convince yourself that that's not a very promising environment in which to produce intelligent life or anything capable of observing that it's in an axion dominated universe. So selection effects must be considered, as was emphasized by Linde already in 1988, but only taken really seriously recently. This theta 0 I've been talking about, the initial misalignment, controls the dark matter density but has little or no effect on anything else. It doesn't affect the values of quark or lepton masses, the number, any of the structure of the standard model except for the theta parameter. Nor does it affect the production of baryon asymmetry, neutrinos. Nothing appears to depend on this variation of theta 0, except for one particular thing, the ratio of dark matter density to ordinary matter density. So we know what measure we're supposed to apply. If we start with volumes, we don't have to get embroiled in questions of baby universe nucleation, unification, supersymmetry, what a landscape looks like, what you mean by probabilities and internal inflation, none of that stuff. It's just straightforward astronomical selection. So the underlying theory here may be right or it may be wrong, but it's hard to imagine a clearer, cleaner case where it's necessary and appropriate to apply anthropic reasoning. So let's do it. Ask ourselves what's involved in making user-friendly structures that life can be happy in from gas clouds. Lots of things can go wrong when you try to do this. One thing that might happen is that if your gas cloud is too diffuse, it might fail to cool, so it sloshes around and remains diffuse. This is what happens, presumably, for the observed dark matter, which is found in diffuse halos. And I apologize for the busyness of this plot, which is the same thing as apologizing for collaborating with Max Tegmark, who loves to cram as much as possible into diagrams and even more. But what's shown here is different kinds of gas clouds that are starting points for gravitational contraction and formation. So these are the kind of perturbations you might get in the early universe, as we'll later make use of. And then you can ask how they evolve in the nonlinear regime to produce or not condensed structures. If the escape velocity is too small, escape velocity is small here and large here, that's also called the virial temperature of the gas cloud. And the gas density is here, the protons per cubic meter in the gas cloud goes up this way. Anyway, you find that gas clouds in all this region don't cool, so they don't form condensed objects. The protons and neutrons in them they fall into the gravitational potential, but then because they have no way of losing energy, they just fall right back out and remain a diffuse halo forever. Another thing might happen if the gas cloud is too tightly gravitationally bound is that it becomes a black hole, and that's not a nice place to live. Another thing that might happen is you start to form stars, and if the gravitational binding to this cloud is not sufficiently strong, all the gas will be swept out by the early supernovae from the first stars, and that removes another region from the user-friendly phase space. And then finally, you might actually produce stars and presumably solar systems, but if they encounter each other too nearly, we'll have climactic catastrophes or planets getting stripped from their stars, and that further restricts the user-friendly region to this tiny region of suitable starting points. By the way, our galaxy could have started from a seed like this, so with a sigh of relief, we notice that it's in the user-friendly region. Okay, so that's what's desirable or necessary to support user-friendly regions. What do we actually get from primordial fluctuations? So we can overlay the fate map of such seeds, which I just showed you, with the spectrum, what we actually get from cosmological models of the primordial fluctuations. And therefore, by doing that, we predict the spectrum of observed galaxies, and also the spectrum of things that fail to be galaxies. And here is what we get with the standard cosmology, the observed fluctuation spectrum of primordial inhomogeneities. It's basically, we can ignore this brown region here. The crucial thing is this one here, and that's the spectrum you get. I won't go into details here, but it nicely intersects this region and actually says something very profound. It predicts the striking fact about our universe and the objects in it, that galaxies have a characteristic size The characteristic size of galaxies is given by the intersection of this, what used to be the white region, with this fluctuation spectrum. Okay. Just to explain what these labels are, as I mentioned before, density goes up here. If you think of them as fluctuations that are entering the horizon at different times, these are the ones that come in later, are the less dense and bigger ones that enter the horizon later. And this parameter corresponds to the density contrast inside the fluctuation compared to the ambient background. So, as I said, and let me emphasize it again, these calculations give a semi-quantitative explanation of the characteristic size of galaxies and the fact that there is such a characteristic size. So far, what we've done is entirely conventional astrophysics and cosmology. With our confidence soaring, we can proceed to consider the effects of varying the parameters, to see in particular what would happen if we made the only change that you do make, if you change the value of this theta zero parameter, if we change the value of the dark matter density. And again, I apologize for Max Tegmark. He tries to cram too much on every transparency, but this is the relevant one. If you increase the dark matter density, fluctuations of a given baryon to photon ratio enter the horizon earlier, so that pushes up this primordial fluctuation curve on the fate map. And now we can implement, even at least in a crude way, the selection effect. We shouldn't be counting every unit of volume the same. We should give some allowance and favor to regions that can actually support the emergence of structure and user-friendly environments. So what we do is count the number of baryons that wind up in that white region, in the user-friendly region. And now we have a result. If we weight things in that way, by what an observer is likely to see, we can ask ourselves, what does the typical observer see, or what's the probability of that observer seeing different ratios of dark matter to ordinary matter? And it works out remarkably well. The observed value of the dark matter per photon or per baryon is remarkably close to the most probable value calculated this way. It's a striking result, I think. The scenario that it came out of, the scenario with inflation after the Peccei-Quinn transition, also removes some annoying difficulties of the traditional alternative. Specifically, there's no longer need to introduce this scale, f of 10 to the 12th GeV, as a new constant of physics. We can make do with the unification scale, or even the Planck scale. Also, for experts, things that could cause problems in conventional axion cosmology, the strings and domain walls get diluted away because we had inflation in between. Now I'd like to discuss very briefly, because I know my time is running out, the testability of this hypothesis, which brings it to the forefront, I think, of current experimental efforts. A canonically normalized boson field, whether graviton or axion, during the inflationary phase, during the de Sitter expansion, feels, crudely speaking, an ambient temperature the Gibbons-Hawking temperature, which measures the scale of inflation squared, basically related to the Hubble constant squared, divided by the Planck mass. And that makes fluctuations in these things that get imprinted. For axions, that translates into jitter in the theta zero parameter, and thus ultimately into isocurvature density fluctuations. Isodensity curvature fluctuations are fluctuations in the dark matter density that are uncorrelated with fluctuations in temperature or baryon number density. When all things fluctuate together, that's called adiabatic fluctuations. Anyway, those two kinds of fluctuations have observably different effects on the cosmic microwave background anisotropies, and one can distinguish them. And one can also distinguish the effect of gravitational fluctuations. So, in principle, one has observables correlated with this physics, and constraints on isocurvature fluctuations as observed, therefore, translate into constraints on the inflation scale, and then, through this line of reasoning, also to constraints on the gravitational wave background. So the upshot of all that is that inflationary axion cosmology would be falsified if we saw the gravitational waves indicating a large value of the inflation scale without seeing the isocurvature fluctuations that would be entailed for the axion field. On the other hand, a theory that can only be falsified, well, that's a theory that might satisfy Karl Popper, but doesn't satisfy people who like to see their theories verified. We want to see how could the theory be truthified. Well, it would certainly help if we still have a dark matter problem after the LHC and WIMP searches do their work. So keep going and keep not finding anything. Or especially if we actually discover the isocurvature fluctuations without gravity waves, we'd have to blame them on something, and axions would be the obvious candidate. Very recently, Arvanitaki and Dubovsky, elaborating on earlier work by them together with Dimopoulos, Caliper, and Marsh Russell, have argued, or I think discovered, a very interesting process that axions whose Compton wavelength is a small multiple of the horizon size of a spinning black hole will, by the Penrose process, develop an atmosphere. Certain so-called superradiant modes will get filled with these massive particles and get trapped as a sort of atmosphere. So black holes no longer have no hair. Spinning black holes have axion atmospheres. This effect alters the gravitational wave signals from these black holes, and would also alter the X-ray signals from matter falling into them in waves that can be estimated. It can also have a very spectacular effect. You make this atmosphere, but the modes keep getting filled because they're super radiant. Eventually the axions start interacting with each other, and they are in an attractive interaction. They would collapse, making something that's the analog of an effect that's famous recently famous in cold atom systems, the bosonova. Since the Compton wavelength of the axion is 2 centimeters for f equals 10 to the 12th, and then proportional to f for larger values of f, whereas the Schwarzschild radius of a solar mass black hole is 2 kilometers, the black holes of solar mass and above provide a promising window through which to view axions with f equal to or greater than 10 to the 15th GeV. I think this is the first realistic prospect for more or less direct observation of that regime. So if careful study of black holes, which is ongoing and becoming very refined, indeed reveals that spinning black holes that are of a certain size, not bigger and not smaller, seem to have atmospheres. We'd discover the solution to the strong CP problem, the solution to the dark matter problem. We'd get very powerful support of inflation because the Axion model would otherwise give too big a dark matter background, and exhibit strong field quantum gravity at work all at the same time. So it's a pretty tantalizing prospect. Okay, I think my time is probably up, right? So I would rather end on that sublime note than the somewhat ridiculous subject of portals, so I will skip ahead to the summary. Oh, maybe I should do it this way. No, I'll keep going. Sorry about this. You're actually not missing a lot of content, but there are a lot of slides. Right. And I think if you read them, they'll be pretty self-explanatory. Gosh, this guy is long-winded. All right. Summary. No, not yet. Oh, well, this one I should mention. Okay. One example, I mean, the whole subject of portals is what I alluded to at the beginning, that because of the structure of the Standard Model and especially the success of this unification calculation, it indicates that the most interesting, to me, I think, the most interesting perturbations to the Standard Model or additions you can imagine have to do with adding either complete SU5 multiplets or particularly SU3 cross SU2 cross U1 singlets. A particularly interesting example of that arises in many models of supersymmetry, in particular in gauge-Eno mediation, is an SU3 cross SU2 cross U1 singlet that turns out to be the lightest R odd particle rather than the lightest R odd particle of supersymmetry being a partner of a Standard Model particle. It's the partners of Standard Model particles, or ordinary particles, ordinary superpartners, that would be produced directly at the LHC. But if they're not the lightest, they would decay into what is the lightest, which could be something more exotic, like a Gravitino, Goldstino, or Axino, something that is the partner of something that's not in the Standard Model. Such slow decays, because they're communicating with funny sectors, might yield unusual collider signatures, and so the thing that you produce might be rather long-lived. It could even be charged and look stable, and yet consistent with strong cosmological bounds against the existence of stable charged particles, because it would be unstable on cosmological scales, time scales. So the loss gets lost cosmologically, and I think that's a very nice thing, because it's been embarrassing all these years to have two good dark matter candidates. So the lost should get lost. All right, so let me summarize. What I hope and expect the future will bring. So my first tier explanations, which I have explained, some version of low energy supersymmetry to consummate the unification, some version of axions to consummate the wonderful story of understanding time reversal in symmetry in the Standard Model, which, among other things, led to the whole machinery of the Kobayashi, Muskawa, Kabibo theory with its spectacular success. Second tier expectations, if we really push things, if we push beta tau unification It suggests that the gluino mass is significantly smaller than the fermion masses, the fermion partner masses, and suggests large values of the tan beta parameter. If we go further into our demand for simplicity of symmetry breaking, that definitely requires large tan beta. Large F gave this beautiful explanation of why the observed dark matter is what it is. It requires isocurvature fluctuations much larger than cosmic gravity waves and suggests the existence of black hole atmospheres. And the loss gets lost. Okay, thank you for your attention. That's my